Hi, in today's video we're going to take a look at how to use a spectrum analyzer to demodulate an AM or FM signal. And here I have my newly acquired HP8566B spectrum analyzer, and this is actually quite a beefy one. It has a lower band of 0 to 2.5 GHz and upper band from 2 GHz all the way up to 22 GHz. And also, along with the spectrum analyzer, we're going to use my HP 8642B signal generator. So this signal generator will be used to generate the AM and FM signal, and we will use that in conjunction with the spectrum analyzer to demodulate the signal. And later on, towards the end, I will show you how to use this spectrum analyzer as a general radio receiver to receive both the AM and FM signals. So before we get started, I'd like to first go over some basic theories on how the demodulation is done using a spectrum analyzer. For AM signals, it's considerably easier and very intuitive on how this is done. So for instance, we have a AM signal sitting on top of a carrier frequency which is much higher than the actual signal being modulated with. And our goal is to demodulate the signal and retrieve the audio component, or the signal component. In this case, is the envelope. So in this case, the whole signal is passed through our spectral analyzer using the zero span frequency feature. In that setting, what we do is we set the frequency to the frequency of the carrier, so the carrier FC, and we are sitting on the carrier frequency FC, looking at the signal. And so what we get really is the variation of the amplitudes over time. And this detected signal passes through a low-pass filter and a detector. We get our actual AM modulated signal. So there's nothing too much to it. So how about FM signal? As it turned out, FM signal is a little bit harder because FM signals have a constant amplitude, or the amplitude doesn't really matter. It's the frequency variation inside this carried signal that is encapsulating the information being transferred. So here, let's take a look at this FM signal. It basically has a center frequency of F0, and the frequency expands, depends on the modulation depth, to, let's say, F0 minus FB to F0 plus FB. And if we plot that with the using the spectrum plot, we get this figure. So basically, this is your kind of like your center frequency F0. So this is your amplitude, this is your frequency. And then we have this F0 minus FB and F0 plus FB. FB. So as you can see, if we use the same technique as what we did with the AM signal, we're sitting on F0 with our zero span frequency on the frequency analyzer, on the spectrum analyzer rather. We are really not going to see much because as the frequency shifts, we get the same amplitude. So the amplitude is going to be a straight line, so we can't demodulate our signal. Well, or could we? As it turned out, we could. The reason for that is because our bandwidth filters have a transfer function. Typically, it's a Gaussian transfer function. So which means the filter has some characteristics, let's say, where towards the center frequency, F0 of the filter, we let all the signals through. Has a very minimal attenuation. And towards when the frequency deviates from the center frequency, we kind of roll off following this Gaussian curve. And so the further away we are from the center frequency, the more attenuation we have. So depending on the transfer function, we can utilize that to demodulate our signal. So now let's take a look at how this is done in the spectrum analyzer. Again, we have this filter bandwidth set by our bandpath filter. And the filter has a typical curve of a Gaussian. So that's actually how most of filters' characteristic curves look like. And let me move this down a little bit. So this one has a center frequency of f0. Our signal passes through because remember the characteristics of this slope. If our signal sits at this frequency, the output amplitude is going to be small. If our output signal sits at this frequency, then after passing through the bandwidth filter, the amplitude is going to be large because it's closer to the center frequency. So we utilize this slope of our transfer function of our bandpath filter we can utilize this to detect our FM signal. So if we have our center, in other words, if we tune our zero span at, let's say, this frequency f1, then this is going to be your 0 point. So then what happened is, if we kind of draw this down here, if the frequency is low, then we're going to get our signal output at the in relation to this reference point going to be negative. If the frequency is high, we're going to have a output of this point, which in reference to that reference point will be positive. So utilizing this slope of the transfer function of our bandwidth filter, we can also demodulate the FM signal. And as you notice, well, because the filter essentially is symmetrical, so we actually can detect the FM signal use either the upper band here, for example, or the lower band. So this is how we're going to be demodulating the FM signal. Later on, I will show an example of that. So the circuit for this type of detection is actually quite simple. You can basically build this in front of your AM detector and make it an FM detector. So for instance, the simplest way to generate this kind of Gaussian-shaped bell curve is to use an LC filter. So we have a tunable LC filter. That's our frequency to amplitude converter. Because this thing has a resonant frequency of f0, so it rolls off, depends on the Q factor and a bunch of other characteristics of your LC. And then, we usually have a resistance somewhere here, R in. So if you have a signal here, if the signal changes in frequency, the output is going to be changing in amplitude because of the LC resonance. So after this, if we pass it through a typical diode detector, I'm not going to draw the, so typically it's a diode followed by a capacitor, and sometimes depends on what you're detecting, quasi-peak detector, you have a resistor at a certain value. But anyway, so then we have our amplitude demodulated signal out here. So now with this background theory in mind, let's take a look at some experiments. Okay, so now I have both my 8560B spectrum analyzer and the 8642B signal generator turned on. As you can hear, they're pretty loud in the background, so I'll try to speak as loud as I can so that you can hear what I'm trying to explain. But anyway, so you can see the setup here. Right now we have this N connector cable coming out from the signal generator to our spectrum analyzer input directly. So I'm going to set up a tone that from the 8642B right now. So let's set let's say 1 gig. The particular frequency doesn't really matter. I'm just setting up a signal here, and the amplitude, let's say minus 40 dBm. And let's come here to take a look on our spectrum analyzer. Right now we're on the range from 2 to 22 gigahertz, so you can't see the signal. So let's change it back to 0 to 2.5. And you can see that the signal is right here sitting in the middle. So let's zoom in a little bit. So I'm going to set my center frequency to 1 gigahertz and set my frequency span to 1 megahertz. And as you can see, this signal is right here. Now, this is a little bit off the center frequency, probably by, I would say, several kilohertz. The reason is that this unit, 8566B, has its own oven-controlled oscillator, and so does my 8642B. And these two are, not exactly on the same frequency, but so that's something we just need to keep in mind. Ideally, you wanted to have a same 10 megahertz reference across all those precision instruments, but for what we're doing here, this doesn't really matter. Anyway, so now we have our 1 gigahertz minus 40 dBm signal. So let's just check that. So minus 39 dBm, and it's right on the mark. So now let's turn on the modulation of the signal. Let me zoom in a little bit. So basically we do AM and we turn it on. By default it's a 50% modulation, and that's good enough for us. And as you can see on the spectrum analyzer, you'll see the signal started to wobble a little bit. That's because of the modulation going on. And I posted on my blog, in a previous blog posting, that you can use your spectrum analyzer to easily determine the modulation depth by changing to linear mode and view the amplitude relationship between the first and your side bands. But anyway, here we're more interested in seeing how this signal can be demodulated. So to demodulate the signal, we wanted to first center the frequency of our marker. So we do marker to center frequency, and then we change the frequency span to 0. So now, as you can see on the screen, I'm not sure you can see here, we demodulated the signal. Now, of course, the signal right now is distorted because we have our setting still as dB. So let me change that back to linear. So linear mode, and we want to set the reference level to, let's say, 10 millivolts. And let's turn off the marker so you can see the actual signal. So the marker, let me first adjust the amplitude a little bit. So this is good enough. So let's turn off the marker, and now I wanted to turn the video filter on. The video synchronization on, so you can see actually the signal here. So now we have demodulated our 1 kilohertz signal. And so next we're going to take a look at how we're going to be demodulating an FM signal. So for the FM modulation, we want to come back here to change 8642B to FM. So right now we're still at AM. I'm going to turn the AM modulation off and turn the FM modulation on. And I wanted to set this FM modulation to the bandwidth to be as high as possible, so that I can actually see that on the frequency on my spectrum analyzer. So I set it to 1 meg. So now let's come back to the frequency spectrum analyzer. Again, right now it's at default. So this is a 0 to 2.5 gigahertz. And again, I'm going to put my center frequency to 1 gigahertz and put a frequency span to 1 megahertz. Actually, right now, because let me lower the frequency band a little bit, because remember we set it to 1 megahertz, which is pretty big. So we set it to 400 kilohertz. So that's our FM signal. Basically, you have it centered at 1 gigahertz, and has a 400 kilohertz either way. So here is our frequency modulated 1 gigahertz signal with a frequency deviation of 400 kilohertz. And we're going to do the same thing as what we did with the AM signal. First, we set the frequency span to 0. And then we are going to set it to linear mode. We then set the reference level to 10 millivolts. So now we can see some signal at the bottom. But remember, we are right now looking at actually the signal that is towards the center of the filter. So we would expect if we change the frequency, either lower, do you see that jumping up, or higher, right here. And you will see that on either side of the frequency band, we can see this demodulated signal. Now, you will say that, hey, wait a minute, this signal, if I just turn the video trigger on, this signal does not look anything like a sinusoid, right? So let's, for you to see it better, let's turn the reference level down a little more so you can actually see the signal stronger. So let's change it to 5. Something like this is good. So if you look at the signal, it's heavily distorted. And the reason for that is right now we're sitting at a resolution bandwidth of 10 kilohertz. And the signal we're running is has a 400 kilohertz frequency deviation. So basically the linearity is really poor for this. And in order to see that more clearly, we need to increase the bandwidth of the observation frequency bandwidth. So let's set it to resolution bandwidth, let's say for 1 meg. And as you can see already, the signal looks much better. So let's just tune it right here. So now you can see, so yeah, there's some glitches. That's basically the display glitch. Has nothing to do with the signal. But you can see that this sinusoidal wave is really looks good. This is right now at a 1 gigahertz 482 kilohertz level, so which is the upper band of our demodulated signal. Equally, we can do that from our lower band as well. So if I just lower my center frequency, if you lower too much, yeah, so lower to 999. So here you can see that once again. Well, this is probably I can do that a little better, like now. Yep. So now you can see that this trigger signal also looks pretty good. So this is our demodulated signal at the lower band. So now we understand the theory of how this is done. We're going to use it to use a spectral analyzer as a really expensive radio receiver to demodulate some real-life signals. So for the next experiment to listen to AM and FM radio, we're gonna use this amplifier which I built. There's nothing particular, it's just a single chip amplifier, and the BNC input comes from the video output from the spectral analyzer. So let me hook that up. Actually, before I hook that up, let me set up the spectral analyzer. So now let's start from testing the AM radio receiving. And for that, I have this antenna. I extended it because I'm right now in my basement, so that I don't think the reception is very good. But hopefully we can receive a few strong stations. So let's set the start frequency to 550 kilohertz and a stop frequency to 1600 kilohertz. So that roughly covers our AM frequency band. And we can see quite a few signals here, and all these are probably just stations. So I'm going to choose the strongest right now for this experiment. So we're going to do peak search, and the center one is good. So I set it to our center and set the frequency span to 0 hertz. So that is our station. Remember, we have to set it back to linear, and we have to set the reference level correctly. So now I'm just going to set it, to 10 millivolts. We can always change it later. 10 millivolts. And as you can see, here's our signal. So if I hook up the amplifier, I would expect to hear something. So let's do that. So right now I'm hooking up the audio amplifier here. So you can kind of hear, so if we
Federal Court in Trenton, New Jersey.
So that is what is coming out from the radio, and we can do slightly better. We can just by changing the reference level, we can change it lower, so that so that our signal level is higher. And we can actually just free tune this, right? So we can just use it as any. So there's a channel here, there's another channel here, there's some interference coming in, and yeah, as I said, I was in the basement, you can't hear a lot of channels here. So that's one channel. This is the strongest channel. So it seems like we only can receive that one channel, but that's the AM radio for you. Let's come back here.
We made those tapes available to Sarah Koenig, podcast serial, Dow Chemical, and the DuPont.
So
they are merging in a $130 billion chemical industry mega deal. The merger calls for the two companies.
And now let's take a look at, after this, we'll take a look at the FM frequency range. So now let's take a look at how to demodulate an FM signal using the spectral analyzer. To do that, we will first set the spectral analyzer to be within our FM broadcasting band, which is 88 megahertz to 108 megahertz. And we can already see quite a few strong stations. So let's just pick the strongest one. We want to bring this peak to our center and set the frequency span to 0 hertz. So now, this is our signal that we'll be dealing with. And right now we first set it to linear and set the reference level to, let's say, I don't know, 5, 10. Let's set it to maybe 3 millivolts. And we have something there. I'm not sure if it's strong enough. Let's hook up the speaker and see what we get. So right now you can hear we have significant distortion from the speaker. That's because, as I mentioned earlier, we need to demodulate this thing either at the lower band or higher band. Okay, so let's. So right now, as you can see, this is probably the lower band of that signal, so we can hear quite clearly. And right now, let's see if we turn this to the upper band. So it's actually very clear. And the lower and upper band is a little bit of touchy because we don't have that, the tuning is only about 20 hertz, 20 kilohertz, the actual frequency. So the bottom line is we're either tuning it to, let me turn it off, it's quite distracting. So it's either tuning to the upper band or lower band. Okay, so now let's take a look at why we need to have such a high resolution bandwidth right now. Right now, the resolution bandwidth set is at 100 kilohertz. So let's see what happens if we reduce the resolution bandwidth. So again, let me hook the speaker on, and let's change the resolution bandwidth down to, let's say, 5 kilohertz. Okay, 5 kilohertz. So now let's change the center frequency. You'll see that you can still hear the radio, but it's heavily distorted because now the slope doesn't cover the actual frequency range. So what you receive in that demodulated signal is only, it's basically severely distorted. So it's a severely distorted. So to fix that, again, we can set our resolution bandwidth to at least, let's say, 50 kilohertz, right? So then we're fine because our, let me again turn it off. So because our FM signal is only occupying roughly 20 kilohertz bandwidth. Anyway, I hope you enjoyed the video today and also learned something new. If you liked the video, please give it a big thumbs up. I really appreciate it. Thanks.